Learning outcomes. After studying this module, you shall be able to know about different ways for the synthesis of metal carbonyl complexes such as photolysis, thermolysis, reductive carbonylation, etc. Introduction. Nickel tetracarbonyl was the first metal carbonyl to be discovered and prepared in the laboratory in the year 1890, which was discovered accidentally when Ludwig Mond observed that nickel balls were eaten up by carbon monoxide gas while passing through them. He considered that it happened due to the reaction between nickel and carbon monoxide. Then he deliberately heated nickel powder in a current of carbon monoxide gas. Consequently, a volatile compound, nickel tetracarbonyl, was formed as a water clear liquid which decomposes around 180 degrees Celsius to pure nickel. Metal carbonyls can be prepared by the direct reaction between finely divided metal with carbon monoxide gas under appropriate conditions of temperature and pressure. Reductive carbonylation of the salts of transition metals in the presence of various reducing agents also leads to the formation of metal carbonyls. The reducing agents that can be used in reductive carbonylation reactions of metal carbonyls are carbon monoxide, dihydrogen, metals such as silver, copper, magnesium, aluminium, sodium, etc., lithium aluminum tetrahydride, and Grignard reagents. The carbon monoxide groups of pentacarbonyl iron are loosely bound, hence it can be used for the synthesis of other metal carbonyls. The photolysis or thermolysis of lower metal carbonyls leads to the formation of higher metal carbonyls. The abstraction of carbon monoxide by metal from organic compounds such as alcohols, aldehydes, and acid chloride, etc., also leads to the formation of metal carbonyl complexes. The dissociation of the metal-metal bond of polynuclear metal carbonyl by dihydrogen leads to the formation of metal carbonyl hydride. The reduction of metal carbonyls by alkali metals, alkali metal amalgams, or sodium borohydride in tetrahydrofuran or liquid ammonia solvent produces anionic metal carbonyls. The acidification of anionic metal carbonyls produces metal carbonyl hydride. The reaction of metal carbonyl halide with carbon monoxide and aluminum trichloride produces cationic metal carbonyl. Heteronuclear metal carbonyl complexes can be produced by the treatment of anionic metal carbonyl with metal carbonyl halides. Nowadays, there are a number of general routes for the synthesis of metal carbonyls which will be discussed here. By the direct combination of carbon monoxide and metal. This method is mainly used for the synthesis of homoleptic or binary metal carbonyls. Many transition metals in the finely divided state can combine with carbon monoxide gas under suitable conditions of pressure and temperature, forming metal carbonyl complexes. However, only nickel tetracarbonyl and iron pentacarbonyl are normally synthesized by this method. Finely divided nickel reacts with carbon monoxide gas at room temperature and pressure, resulting in nickel tetracarbonyl, whereas the reaction between finely divided iron and carbon monoxide gas at an appreciable rate requires elevated temperatures and pressures such as 200 degrees Celsius and 200 atmospheres. Whereas dicobalt octacarbonyl can also be prepared by the direct reaction of finely divided cobalt metal with carbon monoxide gas under similar conditions, but the yield of this product in this reaction is very low. Reductive carbonylation of transition metal salts. The oxidation state of metal in metal carbonyls is generally 0. This is due to the fact that carbon monoxide is a pi acceptor ligand. Any metal carbonyl is stable only when there is a metal to carbonyl pi back bond donation of appreciable strength. It is possible only when metal is present in lower oxidation states, preferably 0 or negative. Therefore, metal carbonyls can be prepared by the reduction of salts of transition metals in the presence of carbon monoxide gas. First of all, the salt of transition metal is reduced to produce finely divided metal. Then the finely divided metal reacts with carbon monoxide, forming metal carbonyl. Various reducing agents can be selected for this purpose. For example, reductive carbonylation by carbon monoxide. When a metal oxide is heated with carbon monoxide gas at high pressure, metal carbonyl is formed, such as in the reaction osmium tetroxide can react with 9 molecules of carbon monoxide at high temperature and high pressure, resulting in osmium pentacarbonyl and carbon monoxide gas. Carbon monoxide acts both as reducing agent and as a carbonylating agent. Reductive carbonylation by hydrogen. Hydrogen gas can also be used as a reducing agent in reductive carbonylation reaction. For example, in this reaction, cobalt carbonate can react with carbon monoxide in the presence of dihydrogen at a temperature of 150 degrees and 300 atmosphere to result in dicobalt octocarbonyl complex plus carbon dioxide and water as side products. Reductive carbonylation can also take place by various metals. Metals such as sodium, silver, aluminium, magnesium, copper, etc. can be used as reducing agent in reductive carbonylation reaction. There are numerous examples for these type of reactions. For example, ruthenium triiodide can react with carbon monoxide in the presence of silver at high temperature and pressure, resulting in ruthenium pentacarbonyl and the formation of silver iodide. Here we can see silver has undergone oxidation, resulting in the formation of silver iodide, and there are numerous examples. We can also do reductive carbonylation by various reducing agents such as lithium aluminum hydride. It can be used as a reducing agent during the synthesis of metal carbonyls by the reductive carbonylation of metal halides. For example, chromium trichloride can react with carbon monoxide in the presence of lithium aluminum hydride at a much lower temperature and pressure, resulting in chromium hexacarbonyl and other chloride salts. Reductive carbonylation by organometallic compounds. The organometallic compounds such as Grignard reagents, trialkylaluminum, etc. can also be used as reducing agents during the synthesis of metal carbonyls by the reductive carbonylation of metal halides. For example, chromium trichloride can react with carbon monoxide in the presence of phenyl magnesium bromide, a Grignard reagent, to give chromium hexacarbonyl. There are other examples also. Reductive carbonylation can also be done by sodium benzophenone or ketyl. For the synthesis of magnesium carbonyl, sodium benzophenone ketyl can be used as a reducing agent, such as examples are shown here. Synthesis by iron pentacarbonyl. The carbonyl group of iron pentacarbonyl are loosely bound and hence labile. They can be replaced by chloride ions on treatment with molybdenum hexachloride or tungsten hexachloride, leading to the formation of molybdenum hexacarbonyl and tungsten hexacarbonyls respectively. The examples are shown here. Photolysis of lower metal carbonyls. Higher metal carbonyls can be prepared by the reaction of photolysis of lower metal carbonyls. For example, when the cold solution of iron pentacarbonyl or osmium pentacarbonyl in glacial acetic acid is irradiated with ultraviolet light, diiron nonacarbonyl and diosmium nonacarbonyls are obtained respectively. For example, the pentacarbonyl iron under UV light results in diiron nonacarbonyl and a carbon monoxide molecule. These reactions proceed through a mechanism. The pentacarbonyl complex under UV light decomposes to a tetracarbonyl complex and one of the molecules of carbon monoxide is abstracted. the tetracarbonyl complex and the pentacarbonyl complex can react to give a dimetallic nonocarbonyl complex product. We can also perform thermolysis of lower metal carbonyls. A lower metal carbonyl can be transformed into a higher metal carbonyl on heating up to an appropriate temperature. For example, two molecules of dicobalt octacarbonyl at 70 degree results in a tetracobalt dodecacarbonyl complex with the release of 4 carbon monoxide molecules. Likewise, 3 molecules of diiron nonocarbonyl at 50 degree gives a complex with a composition triiron dodecacarbonyl and release of excess of carbon monoxide molecules. Similarly, when the solution of diiron nonocarbonyl is heated up to 70 degrees and then cooled, green crystals of triiron dodecacarbonyl separates out. Method of abstraction of carbon monoxide from organic compounds. This route of synthesis of metal carbonyls involves abstraction of carbon monoxide from organic compounds such as aldehydes, alcohols, and acid chlorides, etc. The examples proceed through 3 steps. For example, the reaction proceeds by oxidative addition of the carbonyl containing molecule in the first step, whereas in the second step, a retromigratory insertion leads to the formation of a second complex, and the second complex in the third step undergo reductive elimination, resulting in a final carbonyl complex with the release of a chloromethyl molecule. The second step of the reaction is the reverse of migratory insertion. The success of the reaction depends upon the thermodynamic stability of the final metal carbonyl formed, and it is greater for a low valent metal. In the case of acid chloride, the first step is the oxidative addition of CCl bond, which takes place with great facility. In the case of aldehydes, the first step is the oxidative addition of the aldehydic CH bond, which takes place with difficulty. It is much difficult for a metal to break CC bond, and therefore ketones are reluctant to take part in such reactions. Synthesis of heteronuclear metal carbonyls. The heteronuclear metal carbonyls can be synthesized by following methods, such as by the reaction of anionic metal carbonyl with metal carbonyl halide. The reaction of an anionic metal carbonyl with a metal carbonyl halide of different metals produces a heteronuclear metal carbonyl. Examples are these reactions are generally carried in tetrahydrofuran solvent in which sodium carbonylates are soluble. We can also prepare heteronuclear metal carbonyls by heating cationic anionic metal carbonyls. For example, when a cationic anionic metal carbonyl, as shown in the picture, containing different metals is heated up to suitable temperature, a heteronuclear metal carbonyl is formed with the loss of carbon monoxide. Similarly, we can make heteronuclear metal carbonyls by heating a mixture of 2 or more metal carbonyls of different metals. When a mixture of 2 or more metal carbonyls is heated up to a suitable temperature, a heteronuclear metal carbonyl is formed with the loss of a carbon monoxide molecule. Example is shown here. We can also prepare heteronuclear metal carbonyls by the irradiation of a mixture of 2 metal carbonyls of different metals. When a mixture of dimanganese decacarbonyl or diarynium decacarbonyl dissolved in normal hexane solvent is exposed to light, a heteronuclear metal carbonyl is formed. Synthesis of cationic metal carbonyl. The cationic metal carbonyl can be prepared by the reaction of metal carbonyl halide with carbon monoxide in the presence of a Lewis acid such as aluminum trichloride or boron trifluoride. The cationic metal carbonyls can also be prepared by the protonation of metal carbonyls in strong acids in the presence of Lewis acid such as boron trichloride. NMR spectroscopy indicates that proton becomes bonded to the metal atom in the above reaction. Synthesis of anionic metal complexes. There are four important methods for the preparation of anionic metal carbonyls, such as metal carbonylate complexes. First is by the action of hydroxide ion on metal carbonyls. In this reaction, where iron pentacarbonyl reacts with sodium hydroxide, resulting in an anionic metal carbonyl. This reaction involves the nucleophilic attack by hydroxide ion on the carbon atom of one of the coordinated carbon monoxide molecule, followed by the transfer of electron to the metal atom and the formation of a carbon dioxide. The second method is by the reduction of metal carbonyls. The reduction of metal carbonyls with alkali metals, alkali metal amalgams, or sodium borohydride in tetrahydrofuran or liquid ammonia solvents leads to the formation of anionic metal carbonyls. A few examples are shown here. We can see a large number of reducing agents such as sodium amalgam, sodium borohydride in THF, and sodium in liquid ammonia have also been utilized. We can also make anionic metal carbonyls by the displacement of carbonyl from metal carbonyl complexes. A number of substituted metal carbonyl complexes can be prepared by the displacement of carbon monoxide from a metal carbonyl, such as in these reactions. We can also make metal carbonyl complexes by reductive carbonylation. When niobium pentachloride or tantalum pentachloride dissolved in diglyme solvent is treated with sodium metal in the presence of carbon monoxide gas at high temperature and pressure, corresponding metal carbonyl complex is formed. It is noteworthy here that the neutral metal carbonyls of niobium and tantalum are not stable, but their carbonyl anions are known. Synthesis of metal carbonyl hydrides. Metal carbonyl hydrides can be synthesized by following methods, such as the reaction of transition metal carbonyls with hydride anion sources. In this example, we can see iron tetracarbonyl diiodide reacts with sodium borohydride in THF, resulting in a hydrido iron tetracarbonyl complex. We can also make metal carbonyl hydrides by direct interaction of metal, hydrogen, and carbon monoxide. When finely divided cobalt is treated with a mixture of hydrogen and carbon monoxide gases at 150 degrees Celsius and 50 atmosphere pressure, cobalt carbonyl hydride is formed. The metal carbonyl hydride complexes can also be prepared by the cleavage of a metal-metal bond by dihydrogen. The treatment of dimanganese decacarbonyl with hydrogen gas at 200 degrees Celsius and 200 atmospheric pressure produces manganese carbonyl hydride. They can also be prepared by the acidification of metal carbonyl anions. When a solution containing metal carbonyl anion is acidified, metal carbonyl hydride is formed. Various examples are shown here. Synthesis of metal carbonyl halides. The metal carbonyl halides can occur as neutral molecules, anions, or cations. The reaction between a metal carbonyl and a halogen is the most common method for the preparation of metal carbonyl halide. The metal carbonyl halide can also be prepared by the reaction of a metal halide and carbon monoxide gas. For example, ruthenium tricarbonyl can react with carbon monoxide in methanol at 65 degrees Celsius and 10 atmospheric pressure, resulting in the ruthenium carbonyl complex.
Various methods that are used nowadays for the synthesis of metal carbonyl complexes are direct combination of carbon monoxide and metal, the reductive carbonylation method, synthesis using pentacarbonyl ion. There are also photolytic and thermolytic methods available. On the other hand, the synthesis of heteronuclear and ionic metal carbonyls are being carried out by using different methods which will be discussed in the subsequent slides. First method is direct combination of metal and carbonyl. This method is mainly used for the synthesis of homoleptic or binary metal carbonyls. Many transition metal in the finely divided state can combine with carbon monoxide gas under suitable conditions of temperature and pressure, forming metal carbonyl complexes. For examples, tetracarbonyl nickel and pentacarbonyl iron are normally synthesized by this method. The reaction between finely divided iron and carbon monoxide gas at an appreciable rate requires elevated temperatures and pressures. And the second reaction, dicobalt octacarbonyl, can also be prepared by the direct reaction of finely divided cobalt metal with carbon monoxide gas. Next method is reductive carbonylation of transition metal salts, in which the reduction of transition metal is carried out, followed by the addition to the carbonyl group with the help of various reducing agents such as carbon monoxide, dihydrogen, metals such as sodium, silver, copper, etc., lithium aluminium hydride, organometallic compounds such as Grignard reagents, etc., and sodium benzophenone. Some examples for reduction of metal carbonyl reduction processes are metal carbonyl complexes can be also synthesized by using pentacarbonyl ion, in which carbonyl groups of pentacarbonyl ion are loosely bound and hence labile. They can be easily replaced by chloride ions on treatment with molybdenum hexachloride or tungsten hexachloride, leading to the formation of hexacarbonyl molybdenum and hexacarbonyl tungsten respectively. Next is photolysis of lower metal carbonyls. In this process, lower metal carbonyls are converted to higher metal carbonyls in the presence of sunlight. For example, when the cold solution of pentacarbonyl ion or pentacarbonyl osmium in glacial acetic acid is irradiated by ultraviolet light, diion nonacarbonyl and diosmium nonacarbonyl are obtained respectively. We are going to study the next method, that is thermolysis of metal carbonyls. In this method, lower metal carbonyl is converted to higher metal carbonyl by simply heating to an appropriate temperature. For example, the diion nonacarbonyl can be converted to the corresponding triion complex by heating it at 70 degrees Celsius followed by cooling. One of the routes of synthesis of metal carbonyls involved abstraction of carbon monoxide from organic compounds such as aldehydes, alcohols, acid chloride, etc. The reaction takes place in three steps, which involves the oxidative addition of the organic compound, followed by the reverse of migratory insertion in the second step, whereas reductive elimination of the carbonyl complex takes place in the final step. The success of the reaction depends upon the thermodynamic stability of the final metal carbonyl form, and it is greater for a lower valent metal. In case of acid chloride, the first step is the oxidative addition of carbon-chlorine bond, which takes place with greater facility. In case of aldehydes, the first step is the oxidative addition of aldehyde carbon-hydrogen bond, which takes place with difficulty. It is much difficult for a metal to break carbon-carbon bond, and therefore the ketones are reluctant to take part in this reaction. The synthesis of heteronuclear metal carbonyls can be achieved by the reaction of anionic metal carbonyl with metal carbonyl halide, by heating cationic anionic metal carbonyls, by heating a mixture of two or more metal carbonyls of different metals, and by irradiation of a mixture of two metal carbonyls of different metals. And the examples are, first is anionic metal carbonyl reaction are generally carried in tetrahydrofuran solvent in which sodium carbonylates are soluble. In the second, a cationic anionic metal carbonyl containing different metals is heated up to suitable temperature. A heteronuclear metal carbonyl is formed with the loss of carbon monoxide. Third is when a mixture of two or more metal carbonyls is heated to a suitable temperature. A heteronuclear metal carbonyl is formed with loss of carbon monoxide. In the fourth and the last one, a mixture of dimanganese decacarbonyl and dirhenium decacarbonyl are dissolved in N-hexane solvent, which is then exposed to light to obtain a heteronuclear manganese rhenium carbonyl complex. Next method is the synthesis of cationic metal carbonyl, which achieved by the reaction of metal carbonyl halides with carbonyl in the presence of Lewis base and by the protonation of metal carbonyls in strong acids in the presence of Lewis acid. Our next method for synthesis is the synthesis of anionic metal complexes, which involves four types of processes, and these are by the action of hydroxide ion on metal carbonyls, by reduction of metal carbonyls, by displacement of carbon monoxide from metal carbonyl, by reductive carbonylation of metal carbonyls. Some examples are in the first reaction, the reduction of metal carbonyls with alkali metal amalgams or sodium borohydride in tetrahydrofuran or liquid ammonia solvent leads to the formation of anionic metal carbonyls. From the second reaction, a number of substituted metal carbonyls can be prepared by displacement of carbon monoxide from a metal carbonyl. In the last reaction, when niobium pentachloride or tantalum pentachloride dissolved in diclime solvent is treated with sodium metal in the presence of carbon monoxide gas at high temperature and pressure, corresponding metal carbonylate complex is formed. Next method is synthesis of metal carbonyl hydrides, which further is divided into four types: reaction of transition metal carbonyls with hydride ion sources, direct interaction of metal hydrogen and carbon monoxide, cleavage metal-metal bond by H2, acidification of metal carbonyl anions. Some examples for this type of synthesis are: in the first reaction, sodium borohydride acts as a hydride ion source in presence of tetrahydrofuran. In the second reaction, finely divided cobalt is treated with a mixture of hydrogen and carbon monoxide gases at 150 degrees Celsius and 50 atmospheric pressure. In the third reaction, dimer of decacarbonyl dimanganese is converted to pentacarbonyl hydridomanganese. In the fourth reaction, a solution containing metal carbonyl anion is acidified, metal carbonyl hydride is formed. Our next method is synthesis of metal carbonyl halides. This is further divided into three types according to metal carbonyl halides formed: neutral metal carbonyl halide, cationic metal carbonyl halide, anionic metal carbonyl halide. There is one different method to prepare metal carbonyl halide, that is by the reaction of metal halide and carbon monoxide gas at any certain temperature and pressure conditions.
In summary, we can say that metal carbonyls can be prepared by the direct reaction between the finely divided metal with carbon monoxide gas under appropriate conditions of temperature and pressure. Reductive carbonylation of the salts of transition metals in the presence of various reducing agents also leads to the formation of metal carbonyl complexes. The reducing agents such as carbon monoxide, dihydrogen, metals, lithium aluminum hydride, Grignard reagents can be used in reductive carbonylation reactions. The carbon monoxide groups of iron pentacarbonyl are loosely bound, hence it can be used for the formation of other metal carbonyls. The photolysis or thermolysis of lower metal carbonyl leads to the formation of higher metal carbonyls. The abstraction of carbon monoxide by metals from organic compounds such as aldehydes, ketones, alcohols, or acid chlorides also leads to the formation of metal carbonyl complexes. The metal carbonyl complexes can be transformed into various derivatives such as metal carbonyl hydrides and metal carbonyl halides. Cationic species and anionic species on treatment with suitable reagents. Metal carbonyl complexes also exist as cationic and anionic species as compared with neutral metal carbonyl complexes. Apart from neutral metal carbonyl complexes, they also exist as cationic and anionic species.